This optical diagram shows how a transparent object here forms an image here. Light from a bright monochromatic source emerges from a pinhole or a very thin slit placed at the focus of lens 1, so a parallel beam of coherent light is incident on the object. In this example, the object is a simple grid of 5 parallel slits in an opaque screen. The width of each slit is almost the same as the distance between them. Light diffracted by the slits is collected by lens 2, which refracts it to form the image. Sets of parallel rays leaving the object are focused by the lens to form a Fraunhofer diffraction pattern in the focal plane. This is the first stage of the image formation process. The second stage is the recombination of the light from the diffraction pattern. Light spreading out from every part of the pattern illuminates the whole of the image plane. Because the light from all parts of the pattern is coherent, when these components overlap in the image plane, they interfere. The interference pattern that results is the image. A blocking filter placed in the plane of the Fraunhofer pattern can be used to study the effect of the various components of diffraction, individually and in combination. This narrow slit only allows light from the 0 order to get through to the image plane. This light alone is insufficient to reveal details of the object slits. It simply contains information about the overall extent of the grid. We say that the structure is not resolved. In this case, the blocking filter is opened up to let light from the 0 order and both first orders of the diffraction pattern get through. Now the structure of the grid is resolved in the image plane. In fact, the structure can be resolved by using even less of the pattern. Here, the 0 order is used along with only one first order maximum, and the structure of the object is just resolved in the image plane. This important principle was first discovered by Ernst Aber, who studied these effects in an effort to improve the resolution of microscopes. In order to get the highest resolution, modern microscopes use oblique illumination rather than illumination parallel with the axis. The 0 order is collected at one edge of the objective lens, and the finest detail that can be resolved is that which causes its first order diffraction maximum to be just collected at the opposite edge of the lens. As more of the pattern is allowed to continue to the image plane, the quality of the image improves. This image uses all the available orders, but it would require an infinite number to produce a perfect image, and since we can never collect or even produce an infinite number of diffraction orders within any real optical imaging system, the resolution of any image is limited by diffraction. Finally, it is possible to form false detail in images of structures by using obstructions within the system that either deliberately or accidentally block some information from reaching the image plane. In this case, a filter is used which passes the 2 first orders only, blocking everything else, including the 0 order. The resulting image shows a clear resolution of 9 or 10 transparent slits. There are only 5 slits in the original object, so false detail has been introduced by the filtering. This effect provides the potential for non-existent structures to be seen in microscope images.